All right, let's look at where we are. It's time to finally talk about what it is that we've been doing all these observations and measurements on. And the thing that we've been observing and measuring is matter itself. Okay, so if you can observe it and if you can measure it, then it exists. And this is kind of basically just what the definition of matter is. It exists, it's tangible, and that means that it occupies space. It has mass, it has volume, it's made of things, of stuff. And the stuff that it's made of is matter itself. So matter is anything that has mass or occupies space, which means it can be measured. Sometimes we want to measure it, and sometimes we just want to observe what is happening to the matter. I started out, and at the beginning of the day, the matter that I was looking at was a solid, and at the end of the day, the matter that I'm looking at is now a liquid. Just an observation. Didn't come with any numbers, didn't come with any measurement. So, right off the bat, we have to do this. We have to look at what are the states of matter. These are also known as phases of matter, and matter can exist as either a solid, a liquid, or a gas. Those are the three phases of matter, or three states of matter. There is a fourth. There might even be a fifth. We haven't discovered the fifth yet, but when we discovered the fourth, the methodology that made us say, hey, there's a fourth state of matter would imply that we're on a line heading this way. There's a fourth state. Anybody know what the fourth state is? I'm going to do it again in like about week 10. Plasma is a state of matter that is a highly excited atomic form of gas. But for us, at this point, these three will do. I'm talking about paradigms. Yes, there are four states of matter, but that fourth one is largely inaccessible and not really needed to give an adequate discussion of everything that's going on. So we're just kind of sticking with three for now, but know that that's not completely true. It's not the whole thing. Okay, so matter can exist as a solid or a liquid or a gas. And matter can be pure and exist in only the named chemical that you're talking about. So a lump of gold contains only gold. There's nothing else in gold. And in fact, we stamp the gold to tell you how pure it is in terms of carat. Carat is a measure of purity. So matter can be pure or impure. All right. Pure matter could be elements from the periodic table. They are pure. The elements that are represented on the periodic table, hydrogen, helium, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon, those are all pure. But if you had a sample of fluorine, which is a gas, it doesn't contain anything other than fluorine. And the closer we look, the more that reveals to be true. Okay, so we can have pure material that is just the atom itself. We haven't introduced the atom, so I'm shying away from it to say exactly what it is. But it contains only one kind of atom inside of an element. Or I could take some pure sodium, that's a metal, and I could take some pure chlorine, that's a gas, and if I mix them together under the right circumstances, I could make some pure sodium chloride. We know sodium chloride as salt, okay? And you could have a sample of salt that is absolutely pure, that it contains only the sodium and the chloride in strict 1-to-1 ratios, and there's nothing else in it. We're going to call those things compounds. Compounds are combinations. I'm going to just go with elements right now. Okay. And then I could do something else. I could take a sample of helium. Helium is a gas. Do we know where helium comes from?
The atmosphere?
It actually doesn't. It's a gas, but it does not come from the atmosphere. Anybody from West Texas? Helium comes from West Texas. Comes from like Amarillo. They dig it out of the ground. It's in the fossil record. And it's been trapped below the earth. And you might know that, yeah, a balloon of helium rises, right? So it's heavy, it's lighter than air. And you fill a balloon with it, and if you don't hold on to the balloon, you lose the balloon. So we find pockets of helium under the ground, and then we dig them out. Guess what that means for the future of helium?
It is finite, it will run out.
It's going to run out. And some estimates say it's going to run out in about 60 years. So no more balloons, no more floaty balloons. Is that a problem?
No.
Yes, it really is a huge problem because the floaty balloon market is not important. But there's another industrial application for helium. Anybody know what else we use helium for? Helium is a gas. If you force it together and you compress it and you turn it into a liquid, it's very, very cold. It's the coldest that we can get to absolute zero. And it's the cold thing that we use to cool superconducting magnets. The superconducting magnets that are required for, what's the big, strong magnet in town used for? We live in a city. This city's got dozens of these.
Construction.
Mm-hmm.
Computers.
Big specialized computers. MRI.
Like
imaging, medical imaging. Are you happy with the fact that medical imaging is going to go away in 60 years' time? No. So, yeah, every time I see somebody release balloons on purpose, I go, oh, you know, that troubles me. Anyway, so if I get a balloon of helium and I get a balloon of oxygen, oxygen is another gas you might have heard of, it's a gas, and somehow I manage to squeeze the contents of this balloon and that balloon into a new balloon. I have a balloon that contains helium and oxygen. This is no longer pure because it's not just one thing. And it's not this description either, because the helium and the oxygen haven't combined together to make anything new. They still are independent of one another.
Does that make it a mixture?
That's a mixture. That was my next question. What would we call two things that you put together that don't interact with each other? That's a mixture. So a mixture is two or more components that occupy the same space but don't interact. And I'm going to add a word to the end of this that we don't know the complete meaning of yet, chemically. One of the things that we'll learn towards the end of the term is that you can mix two gases together, and those gases are completely independent of each other inside of a mixture. And we can calculate with precision how much pressure each one of the gases is exerting inside a container. It's a mixture. And mixtures fall into two categories, 2.5 if you squint. Mixtures can be homogeneous, or they can be heterogeneous. The genius part, well, I don't 100% know what that means right now, but maybe I can figure it out. But homo and hetero mean same and different. What could the same and different be referring to? On the board. The same. No, once you mix them together, they're essentially now the whole thing gets to be impure, right? You're only pure as long as you're only amongst things that are the same as you. If I mix you in with something else, then even if that one was, if this is pure and that's pure, and then you mix them together without combining, but you mix them, well, the whole shebang is no longer pure. Same, different. These. Homogeneous mixtures are made from things that are in the same phase, in the same state. So if I mix two liquids together, two solids together, two gases together, then I make a homogeneous mixture. If I mix solids and liquids together, then I get a heterogeneous mixture. Now I said there's not two types of mixture, there's actually three. So there's a little bit more nuance to it. It's a little bit more difficult than that, but that's a good place to start. That if they're in the same phase, you're likely to make a homogeneous mixture. If they're in different phases, you're pretty likely to make them be heterogeneous. So we could think sand and water makes mud. Mud is a heterogeneous mixture. There's a special thing about mixtures that if at the beginning of the class I said, here we go, here's a plate of sand, no, here's a bowl of sand and a bowl of water, and I mix them together and make mud, and I say, before you leave, I need the sand back and the water back. The thing with mixtures is you can separate them. Mixtures, because they are not interacting chemically, which means that we're going to do something at an atomic level, then you can always reverse the action. You can always get the components back. Mixtures can always be separated. So if I gave you mud and said I wanted water and sand back, what would you do?
Drain the sand.
How would you drain it?
And poke holes or something.
You'd poke holes in something.
Which is get the water out.
Okay.
Or evaporate the water.
Oh yeah, you could do that too. So there you go. You're coming up with a million ideas. We could either evaporate the water off. We could warm the water up. I don't know. You'd have to boil it, and then the water would be lost to the atmosphere. Or we could just get a t-shirt and throw the mud on the t-shirt, and the water will drain through the t-shirt, and the mud as sand will stay behind. Could just filter it. Okay. I'm going to write here somewhere. So homogeneous. In the same phase. Heterogeneous. Oh. Different phases. This is a good start point, but it is not the end. It is not the end of the discussion, because there is a special case. There's a special kind of mixture. It's called a solution. And solutions pop up and defy the classification of what goes in has to come out. So a solution is when you mix two things together and they disperse into each other so finely that you can no longer see it. It becomes invisible. And that can happen in both of these cases. It can happen in both. Okay, let's think. If I had a bowl of glass and a broken glass and a bowl of water, and I mix those two together, what's that going to look like? I'm going to have some water with some glass at the bottom of it. Which one of these is that?
A heterogeneous.
That's this.
Mixture.
That's a heterogeneous mixture. If I wanted to get the shards of glass out of my water mixture, I would just filter it. If I took a bowl of sugar and a bowl of water and I mixed them together, what would that look like?
To the, like the naked eye anyway, it would look like it's all like one liquid.
Yeah, it looks like the original water that I started with because the sugar becomes invisible. It disperses so finely that the naked eye can no longer see it. That's our definition of a sugar, of a solution. Okay. Does that mean that the sugar is lost to me forever? If I run the sugar water through a t-shirt, can I trap the sugar? No. What do I have to do to get the sugar back? I have to evaporate the water off. Yeah, if I boil too hard, I end up with caramel or something like that. But if I evaporate the water using a low heat, then I get my sugar back. So mixtures can always be separated. Always. Sometimes it just takes a little bit more brain power than others. Okay? They can always be separated. So in the solution, the two components disperse so finely. I know I'm writing at the very bottom of the board, and that might not be the best visibility for you all. The two components disperse so finely, they become invisible. Okay. What if I had a bowl of water? Water is what color is water? What color is water? It doesn't have a color. Water has no color, so we call it colorless. Water is a colorless liquid. Okay. What other colorless liquids are you familiar with? How about vodka? If I had a bottle of water and a bottle of vodka, let's say half a bottle of water and half a bottle of vodka, and I mixed them together, what does it look like?
Water.
It looks like the bottle of water and or the bottle of vodka that I started with. Because the water and the vodka have mixed together. They belong in the same family. They're related to one another, and they mix so well that we can't see the transition, can't see the partition. So, sugar and water making a solution. Technically, we started in the heterogeneous world, but a solution is homogeneous. It's all now in one phase. And alcohol and water, we started out as homogeneous and we end up as homogeneous. Okay, so solutions are, there's only one phase. It is what it is. Okay. So the more you read and the more you look in the text or online, I think it's mostly at the high school level, you get like dozens of questions thrown at you. Well, what if I mix that with that? What is that, homogeneous or heterogeneous? And there are some cases right in the middle where you just kind of scratch your head and say, it could be more than one thing. I believe it's our book that said, you all know what compost is, right? So it's leaves and dirt and twigs, and there might be some stray stones in there. And they'll say, well, what's that? Now, in my book, that's a homogeneous mixture because everything belongs in the solid phase. And then your textbook says, oh, it's heterogeneous because the twigs are big and the soil is, the particles of soil are small. So there's a school of thought that says go by size. There's a school of thought that just says just go by phase. You go by phase, you're closer to what the definition is supposed to be. Okay, so if, as you're reading, you come across something and you think, yeah, that doesn't make complete sense to me, ask. Okay, let's look at the elements, because that's where we want to be. Okay. Before I get to the elements, I'm going to do a little bit of a story. We have to define another word first. I'll put it up and I'm going to take it down. It's going back up again in a minute, but I'm going to say one word before it. And the word that I'm going to say follows on from what we know about density. Okay, so density was defined as mass per volume, mass divided by volume. And it turns out that if I find a couple of things that are roughly the same size, oh, that might work. This object and that object are roughly the same size, right? With my eyes closed, I could say, yeah. I understand its volume and its mass. Oh, that's different. Can tell the difference because density is characteristic of pure materials. And this again is an ancient Greek conversation. This is an ancient Greek observation where Lucretius and Democritus were pondering on the state of the universe, and the conversation went along these lines. It is clear that a block of gold is gold, and that a block of copper is copper. And if you know what gold looks like, it's kind of shiny, orangey gold color. And if you know what copper looks like, it's more pinkish. It's got a different color to it. And they said, if these things are pure, and I can tell the difference because I can see them, and I can tell the difference with my eyes closed, because gold is, for the same size, gold is significantly heavier than copper. It's like 3 times heavier. And if I chop those blocks in half and I look at them, this one's pink the whole way through, and this one's gold the whole way through. So they're uniform. This one is made entirely out of matter that is copper. It's copper matter. And this one's entirely made out of gold matter. And if I chop it again and again and again, this one, when I've made it dust, I can still tell the difference between gold dust and copper dust. That there's something about them. I can see that there is something about them that is different. There is something in their character that is different, that it makes them unique. And the question gets to be, how far can I grind the dust down and it still be gold? And about 2,500 years ago, they said, I bet you there's a limit where you can't get any smaller. We should call that the atom. I think there's a sense that the atom is a modern discovery. And in a way, that's true. That atoms were proven to exist about 120 years ago.
I believe it was the Gnostics, right? Philosophy.
Okay, I don't know anything about that. You got no, no. You can tell us, but I don't know. I don't know.
It's just a school of thought that the people who came up with the atom were a part of, one of the philosophical schools.
This was proposed thousands of years ago. So our atom, by definition, is the smallest indivisible particle. I can tell you the names of the guys who are credited with coming up with the concept. Lucretius and Democritus. And I have a wafer-thin little book. It's a manuscript by Lucretius on the nature of things, which I've never read, should read it, in which he says, there's an atom. We're going to make the atom the smallest indivisible particle. Okay. Now we can talk about elements. Elements are on the periodic table, and an element contains only one kind of atom. And our elements are displayed to us on the periodic table of elements. As an outsider, when you look at the periodic table, you go, oh, well, first of all, it's an awkward shape. And then second, it seems to be loaded with code. And I'm a little resistant to learn any of this because I don't see the upside to it. But it turns out that the people who constructed the periodic table for us have done us an enormous favor because it has decoded behavior that the atoms that are placed on the periodic table are placed in sequence and grouped by behavior. So there are a number of times that it comes up through your chemical education where you're asked a kind of difficult question. And instead of figuring it out, you can just look at the periodic table and read and decipher what that means. And it will tell you, oh, that's what that means. So, periodic table of elements. Was started by a guy, wasn't finished because when Mendeleev put this together, bunches of the atoms hadn't even been discovered yet. Some of the atoms on the periodic table are ancient. We've known about them for a very, very long time. Ironsmithing has been around for thousands of years. Goldsmiths have been around for thousands of years. You can go back and look at look at Egyptians. They're finding new tombs all the time now. They've started digging in, actually not very far from existing tombs. They're finding all sorts of stuff all the time. And we're finding gold jewelry from 3,000 years ago. So gold is on the periodic table. It's AU, it's position number 79. We've known about it for thousands of years to the point where you can dig it out of the ground, purify it, and then melt and mold it into shape. So some of these elements are very well established, and some of them are very new, like in the past 40 years new. especially the very, very heavy ones. We're just filling in the blanks now. Okay, so Mendeleev put the periodic table together, and atoms are listed sequentially. Okay. And grouped by behavior. Let's look. When I say that these atoms are listed sequentially, if I pick any box, and the first one I've picked has an H in it, do we know what H stands for? That's hydrogen. That's our simplest, smallest atom. And inside the box, there are three things. There's a number at the top, there's a symbol in the middle, and then there's a number at the bottom. The symbol, it's called an elemental symbol, is either a single capital letter or it is two letters, and the first letter is capitalized and the second letter is not. These ones here that have three letters in them that are not filled in, they're empty. Those have now all been named as something else, and they all now have two-letter symbols. This literally means unium, which means 110, and that is that one's unium, which means 111 and 112 and 113. Okay, these are placeholders for the atoms that we knew we were going to discover, but hadn't found yet. These are all known now. Okay, the number at the top, and we read the periodic table top to bottom, left to right, the way that you would normally read text. The number at the top goes 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. It runs sequentially. These numbers run sequentially. That top number, the one that's an integer, do we know what an integer is? It's a whole number. That top number that is a whole number is called the atomic number. The atomic number tells us where you sit on the periodic table. It tells us something very, very important about what's going on inside the atom itself. Then we have a symbol, and then below it, there is a number. And this one is 1.00794. Oh, here we go. Follow on from a couple of days ago. How many significant figures?
6.
That's 6 significant figures, which would indicate to us, now little proto-scientists, with scientists in the making, 2 numbers inside that box. One of them is 1, and the other one is 1.00794. Which of those 2 numbers has been measured? The one with the precision in it. We get precision in numbers when they've been measured. So that is a measurement of something. The other number is just, the other number has a very, very important meaning, but it's just a count. It's just, I counted 1, I counted 2, I counted 3, I counted 4. The 1.00794 tells me somebody measured that and measured it precisely. When we look at helium, number 2, the number at the bottom is 4.0. 4.00260. How many significant figures in that? A bunch of zeros in there. Do they all count? These zeros are between two numbers, so they count. And that zero, the one at the end, is behind the decimal and behind a real number. So they all count. They all count. So that's been measured as well. But that first number, 1.00 something, and this one, 4.00 something, if we were just to pretend that it's 1 and 4, and I read 1, 4, it's almost 7, it's almost 9, it's almost 11, it's almost 12, it's almost 14, it's almost 16, it's almost 19. Do they read as being sequential? No. No. But they are increasing. The trend is that they're increasing, right? And then this number just keeps getting bigger and bigger and bigger. So both numbers increase, but one of them increases in increments of absolutely one at a time, and the other one increases with precision in intervals that don't completely make sense. So the interval between atom 1 and atom 2, from 1 to 4, is 3. And the interval between atom 2 and atom 3, from 4 to 7, is also 3. But then from 3 to 4, we go from 7 to 9. So the interval is only 2. If you count the interval between the atoms, it kind of goes up and down a bit. Seven, 9, 4, right? Okay, so here are our 3 labels that are inside an element on the periodic table. We have a symbol in the middle, and that symbol can be either a single capital letter or 2-letter notation in which the first letter is capitalized. There's an atomic number at the top, and there's a mass number at the bottom, and the atomic number at the top is an integer. It's just a count. And it's sequential. That the boxes on the periodic table click up 1 by 1 by 1 in their atomic number. And the mass number at the bottom is precise, which means it's been measured. The fact that it has precision means somebody has measured that, not just counted it. And it is non-sequential. But whatever that number represents, whatever it is that we're counting, it does not change by equal increments between atoms. Okay. Okay. So the periodic table is an awkward shape it's got a little block here that are 2 atoms wide, and then a block here that, if we count them, is 10 atoms wide, and a block here that is 6 atoms wide, and then a skinny, long horizontal block at the bottom. It actually doesn't belong there. It's like when you see a map of the USA, and then somewhere in the top and bottom corner they stuff, well, this is where what Alaska looks like, and this is what Hawaii looks like. They are actually attached. We know that they're attached because look, 55, 56, 57, 72. Oh, this goes to here, and then we read all of that until we get to lutetium at 71, and then it leads to hafnium. So the periodic table actually is much, much wider than this. These atoms here are so rare that you're never going to come into contact with them. This is where the plutoniums and the uraniums of the world are. You're not going to come into contact with these atoms. They are very, very rare. And if we included them in the shape that the periodic table demands of us, then the periodic table would be really, really wide, and the fonts that we had to use to put the detail in would be incredibly small, and it would be difficult to read. So we've taken that out and saying, you're Alaska, we're going to put you somewhere else on an insert. Okay. This is called the S block. This is called the P block. This is the D block. Oh, S, P, and D are lowercase. I know I write in uppercase all the time, but they're lowercase letters. And then this skinny one at the bottom is the F block. In general chemistry, we concern ourselves with the main block of the periodic table. The main block of the periodic table is the S block and the P block combined. We're going to talk occasionally about the D block, which are also known as transition metals. But we're going to spend most of our time concentrating on the S and the P block. And if you look at our periodic table, there are little blue sticky notes at the top. And we're going to group the main block this way. 1, 2, 3, 4, but the pen doesn't work. 1, 2, 3, 4, 5, 6, 7, and 8. These are groups, and groups are vertical columns. The other thing that we will look at that are also numbered are called periods. And periods are horizontal. So having a period and a group means it is possible for us to give you these as coordinates and say things like, what element is in group 3, period 2? Group 3, period, what did I just say? Group 3, period 2? Okay. Group 3, period 2. So you would count across until you found group 3, And then you would go down until you went to period 2, and you would find that that is a B for boron. Okay? Monday, we're going to come inside this box and discover what those numbers mean. Because there's something smaller than an atom. The subatomic particles reveal themselves in what those numbers mean, and we'll do those Monday. Have a great weekend. Let me know if anything doesn't go exactly your way.
Have a good weekend.
Bye-bye.
Sorry for that getting awkward.
No problem.
Second.
No problem. Not at all.
Have a good day.
Yeah, you too. So who's our most famous Gnostic then?
Can't remember.
Now,
I'm